Welcome. The topic we'll be discussing in this lecture is creating stack using dynamic memory allocation. So in the last lecture, we have discussed implementing stack by using structure. Okay. In this class, we'll be discussing like how we can create a stack by using dynamic memory allocation. So, so the same type of structure we are defining, and before that we are using the keyword type def because we want to create our user defined data type. And this structure contains only one element, that is key, which is of type integer, and element is the new data type that we are creating. So element is the user defined data type which is getting created. Now for this element type we are creating a pointer, and the name of the pointer is stack. So previously we have used integer pointers, floating point pointers, all that thing. Okay. So when you say int star p, it means that p is a pointer to an integer. That is, p can hold the address of an integer. Similarly, when you say element star stack, it means that stack is a pointer to element. That is, stack can hold the address of an element. Right? And what is element? What is element? Element is a structure which contains only one member called key. So how much size does this element needs? That is a question. So integer means we say 4 bytes. So how much size does this element needs? An element is a structure. So how many size does a structure needs? So there is no standard, what you call, number for the memory requirement of the structure. The memory requirement of the structure depends on the members, how many members are there and what are their data types. So, so you have to sum up all the members data type. So that will be the size required for a structure. Say for example, here there is another character variable, C also is here. Then element will occupy how much bytes? C will occupy 1 byte. That is, character will occupy 1 byte, and key integer will occupy 4 bytes. So every member of this, every variable of type element will occupy 4 plus 1 5 bytes. Okay. But in our case, the the structure contains only one member, that is key, which is an integer. So so when you create a variable of type element, it needs only 4 bytes, right? Okay. So this is a pointer. Stack is a pointer which can hold the address of an element. So this statement, basically what it will do in the sense, it will create a pointer. The name of the pointer is stack. The name of the pointer is stack, and this can hold what? This can hold the uh, address of the element. Okay, one element, and where each element occupies 4 bytes. Okay, this also will have an address. So let us assume its address. The address of stack is 2000. Okay. Right. Now here dynamically we are going to create a stack. What does it mean? It means that initially the size of our stack will be only, the capacity of the stack will be to hold only one item. Okay. So that means in this stack you can only push one element, right? So when you try to push the second element, the the stack is full. So whenever the stack is full, the stack size will be doubled. So initially the capacity is 1. So this capacity will be multiplied by 2. That is, it will become 2. So accordingly, we'll allocate more memory. So now it will become 2. Okay. Now one more element can be pushed. So one more element, second element can be pushed, but you cannot push. But when you push the third element, again stack is full. So whenever stack is full. So whenever stack is full, the stack size will be doubled. So previously, now it is, the stack can hold two elements. Now it will become 4. So again, we'll increase the size of the stack such a way that it can hold 4 elements. Already 2 elements are there. Now it will accept 2 more push. Okay. But again, if you try to push the fifth element, stack is full. So once again, now stack will be doubled. So currently it can allow 4 elements. So now it will become 8. Okay, so it can hold 4 more elements, 1, 2, 3 and 4. That means it will allow 4 more push. Again after that it will, if you try another push, again stack is full, again it will be doubled, 16. Okay, so this is how we are going to do. Okay, so it means dynamically depending on the requirement the memory is allocated, but whenever we allocate the memory is allocated twice of the previous allocated capacity, right? So how can we do that? That's what we are going to discuss here. Okay, so first we have created a pointer. Stack is a pointer which can hold the address of the element. Then initially we know that the capacity of the stack will be 1. So this capacity variable is assigned with 1 and top is assigned with -1 because initially stack is empty. So stack does not have any item. Okay. Now, first, when you begin the program also, stack should be, you should be able to push one element in the stack. That is, there should be, the capacity of the stack should be 1. So for that, we are writing this statement. Stack is equal to element star malloc size of element. What is element? Element is a data type, user-defined data type, which is a structure, which is a form of a structure which contains only one member key. So what is the size of element? Then the size of this structure is 4 bytes. Okay, so it means that it will allocate 4 bytes. These 4 bytes will be will be will be converted to an the address of this 4 byte will be stored in stack. Okay, the starting address of this 4 bytes will be stored in stack. Okay, so before that we are doing this typecasting element star, that is whatever the memory allocated, that will be whatever the memory allocated, that will be addressed by an pointer. Okay, that will be addressed by an pointer, and this 4 bytes is not an integer. This 4 byte is not an integer, it is of type element. Okay, it is of type element, and the starting address of that will be stored in stack. Okay, so already we discussed stack. Initially stack is a pointer. Initially we created stack, which is a pointer, and stack will have some address. Say the address of the stack is 1000. Now when you do this malloc size of element, when you do this, some 4 bytes of memory is allocated, where this is an where this is of type element, and let us assume its starting address is 2000. Its starting address is 2000, and this needs how much bytes? 4 bytes of memory. So that starting address will be stored here. 2000 will be stored here. Okay, it means that stack is pointing here. So this is your stack. Now stack can hold only one element. Now if you perform a push, now says something you are pushing here. So each element has a key. So say that we are pushing such a way that key value is 2. Okay. Now second time if you try to push, stack is full. But what we discussed, when you try to push, the stack size should double. Okay, that is currently its capacity is 1, it should become 2. That is, it should be able to hold one more element. For that we are using this function stack full. So whenever you try to push, if the stack is full, then the stack full function will be called. What it will do, it will say that we are doubling the stack from so and so size to so and so size. Initially it is 1, capacity is 1, now it will become 2. Okay, and then here we are using realloc function. Realloc, which should be realloc? Whatever stack is pointing, whatever the pointer stack is pointing, that should be realloc. So by default, the first argument of realloc type, the first argument is a pointer. But if you refer the syntax, it is a void pointer. It is a void pointer. Okay. But so void pointer is one which can point to any item, but you have to typecast. But here this void pointer is should point to and type of element. So we are typecasting this to element star. Okay. It should point to an it should point to an address of an element. Okay, so we are making it element star. Then how much it should be, the size should be, how much it should be increased? It should be doubled. So 2 into capacity. What is capacity? Previously it is 1. Okay, It's 2 into capacity into size of element. Size of element is 4, capacity is 1. So 2 into 1 into 4 is 8. So previously 4 byte is allocated, now 8 byte. That is another 4 byte will be allocated. The originally allocated 4 will be retained and its value also will be retained. Okay. And capacity is now increased, now multiplied by 2. So now the value of capacity is 2, not 1. Previously it is 1. So capacity equal to capacity into 2. That is capacity is equal to 1 into 2. That is 2. Right. So now another value you can push comfortably here. So now you can push another value like k is equal to 4. Okay. But if you try to push one more element 3, then again the stack is full. So once again, whenever stack is full, the stack full function will be called and the memory will be reallocated. So once again, it will reallocate memory. Now how much it will allocate? This whatever stack is point, it will be reallocated by 2 into capacity. Now what is capacity? 2. So 2 into 2, 4. Size of element is always same, that is 4. 2 into 4, 4 into 4, 16. 16 bytes will be allocated. Already 4 bytes allocated, another, sorry, already 8 bytes allocated, another 8 byte will be allocated. So totally it is 16 bytes. That is another 2 elements it can hold. So the starting address of the second element will be 2004. Okay. The starting address of the third will be 2008. The starting address of the fourth will be 2012, like that. Okay. So, so, so now you can perform two more push. So another value of key may be 1, the next key value. Okay. Next key value may be say 8. Okay. Okay. So fifth time if you try to push, again stack is full. So now stack will be doubled. Already it has 4 element. Now it will become another 4. Okay. So like this we are going to do. So this is what we are going to do in, this is how we are going to make the stack to grow dynamically whenever stack is full. It is whenever the stack get filled, it will, the size will be doubled. Right? That's what we are going to discuss. Okay. So this is the statement which will initially allocate memory for holding one item in the stack. And whenever the stack is full, this particular function will execute and it will double the stack size, retaining the original memory location and its original value. Okay, right. And what are the other functions we'll discuss. So push, this is the push function, which will take an element of type E. So before pushing, we check whether the stack is already full or not, is full. Okay, this is very similar. The code for is full is very similar as that of the normal stack. Okay, so in is full, just we check whether whether top is equal to what you call, whether the top is equal to capacity minus 1. That's it. Okay, there we used stack size, but here capacity is the one which represents the size of the stack. Okay, whether top is equal to capacity minus 1, then it means stack is full. Whenever the stack is full, we make the stack to grow. We dynamically ensure that the stack is grown by calling stack full, which is this. So once stack is grown, then we perform the push operation. If stack is not full, then directly we perform the push operation. Okay. So how we are pushing? So let us assume the initial case. Initially, what is initially stack is a pointer. Initially stack is a pointer. Okay. So if there is a memory for stack, okay, so stack is a pointer, so it will also have some address. Say its address is 2000. Okay, so when you using malloc, say when you first use malloc, 4 bytes will be allocated where one element of stack can be stored. So this will also have a starting address. Let us assume its starting address is 3000. Starting address is 3000 and its ending address will be 3003. Okay, now, so that is I'm talking about this particular statement, stack equal to element star malloc size of element. Okay, so that memory is allocated and that starting address will be stored in stack. Okay, stack is a pointer. It means stack is pointing here. It means stack is pointing here. Okay. Now this new element, whatever the new element, which is an variable of types element, that is e is a variable of type element, it should be placed here. Okay, that is that should become the value of this location. So how can we do that? For that we are writing this statement: stack plus top. What is stack? What is stack? Stack contains 3000. 3000 plus top. What will be top initially? Initially top will be -1 because initially stack is empty. But now we are going to push one element. So we are doing pre-increment plus top. So when you do plus top, it becomes 0. Stack is what? 3000. So it is 3000 plus 0. 3000 plus 0. What is 3000 plus 0? 3000 plus 0 is nothing but 3000 because it is 0. So even if you apply the scale factor, nothing happens. Okay. So this gives 3000. That is this address. But where we want to store? In this location. So we are using store. So the value at this location will be E. So whatever E we are passing, that will come here. Okay. Okay. So next round, once again, if you push, what will happen? Once again, if you push, it is already full because as of our capacity is 1. So stack will be doubled. So now when doubled, in the sense, one more byte, one more uh, uh, set of 4 bytes will be allocated where another element can be stored. Okay. Now if you try to push another element, what will happen? Stack is again 3 plus top. What is top now? Top is now 0. No more it is -1, now 0. So now it will be 3000 plus top means previously it is 0, now plus top becomes 1. Okay, 3000 plus 1. 1 into 4. Okay, that is scale factor is 4 because each element occupies 4 bytes. So 3000 plus 1 into 4 is nothing but 3004. So that is in this location. In this location, the next element will come. Okay. So here the next element will come. Right. So maybe we can call it as E2 or whatever it may be. So like this function works. Right. So that is store, not just value at that location. Okay. 3000 plus 4 gives this location, but that value, in that value, this should come. Okay. Fine. So that is about the push function. And coming to the pop function, in pop we check whether stack is empty or not. If stack is empty, we call stack empty function, which will be similar to the normal stack, which we created without using dynamic memory allocation. So this function will just display that stack is empty, nothing can be popped, that's it, and it will exit, come out. Okay. Otherwise, it will exit of the program because if stack is empty, then you can't do anything, right? If stack is not empty, then what we do? We pop the topmost element from the stack. Okay, for popping, what we are doing is stack plus top minus minus. Why we are doing this? Assume that stack contains 2 elements. Okay, say the one is E0, another one is E1. Okay, E0 and E1. So what will be the top value? Top will be uh, top will be by this time. What will be the value of top? Top will be 1. Okay, because 2 elements are there, so top will be 1. Okay, when stack is empty, top is -1. When one element is there, top will be 0. When 2 elements are there, top will be 1. Okay, so stack plus top. Stack is that pointer, that what we have discussed previously. Stack is that pointer. This is stack. So that stack contains what? 3000. So stack contains 3000. What is plus top? Stack plus top is 3000 plus 1. 3000 plus 1. Okay. 3000 plus 1, that is nothing. 1 scale factor is 4. So it is 3004. Okay. So that is the starting address is 3000. Starting address of the first element is 3000. Starting address of the next element is 3004. Okay. But E1 is a element, is a something of type element. Okay. but we want the value. This is returning an integer value. So that is we want the key value. Okay. So normally when you use structure variable, we access that value as e dot key, like that we access. Okay, that is when we use a structure variable. But this is not an ordinary variable, it is a pointer variable. Okay. So using a pointer when you access a structure, instead of dot operator, you should use arrow operator. Okay, please note down this. When we access the when we access a structure using a pointer, then instead of dot operator, we have to use arrow operator. That's the reason here we are using arrow. Okay. And then what we are doing also stack plus top minus minus, that is arrow of key. So this will refer to this particular address 3004. So in that address, whatever the key value, that key value it will return. Okay. Whatever, if the key value is 4, it will return. Otherwise, whatever it may be. After returning that, top will be decremented. Top will become 0 because one element is popped out. Right? Okay. Similarly, after removing the next element, top will become -1. Right? So this is how we implement the stack using dynamic memory allocation. Okay. So let us see the complete program. I'll show the program in the notepad for clarity. Then we will execute that in WSL. Okay. So these are the required header files stdio.h and stdlib.h. So this is the typed of structure with one member key. We are creating a user defined data type element for that. And for element, we are creating a pointer stack. And the initial capacity of the stack is 1. So capacity is initialized with 1. Initially stack is empty. So stack is top is initialized with -1. This is the function is empty to check whether stack is empty or not. So if top is less than 0, that is, or else you can also write top is equal to -1. So top will become less than 0 only if it is empty. If top is less than 0, it returns 0. It returns 1, which means stack is empty. Otherwise, it will return 0. Is full. So this is to check whether the stack is full or not. If top is greater than or equal to capacity -1, stack will be full when top is equal to capacity -1. Okay. It will never become greater than or equal to greater than capacity -1, but this logic is right. Okay. Or you can write if top is equal to capacity -1, then return 1, which means stack is full. Otherwise, return 0. Okay. So this is the function which will be called when stack is empty. So when stack is empty, it will just display stack is empty. But when stack is full, we should double the stack size. So it will first display doubling the stack size from capacity to capacity into 2. Then we are increasing the stack size by using this statement. Stack is equal to realloc element star stack comma 2 into capacity into size of element. So that much we are increasing the size. So this is what we have already discussed there. And also capacity value we are updating. Initially when capacity is 1, now it will become 2. If it is 2, it will become 4. If it is 4, it will become 8. If it is 8, it will become 16. So on and so forth. Okay. Then this is the function for push. Here we check if it takes an variable of type element and we check whether stack is full or not. If it is full, then we double the stack size. So here when you double using realloc, what happens in the sense the originally allocated memory and its value will be retained. Okay, and then new locations will be allocated. And whatever the new value we want to push, we push in the appropriate place by using this statement. Star stack plus top equal to E. And this is the code for pop. If it's empty, if the stack is empty, then you cannot pop. Then we say stack empty and we exit. Otherwise, we take the top value and we return that. So here stack plus top, we are using arrow key because it's a pointer. That is when you access a structure using pointer, you should use the arrow operator. Okay. So use arrow operator access structure elements to access structure elements using pointer. Okay, so that is the syntax which C follows, right? So that's why we are using arrow here. If it is not a structure variable, if it is not a pointer variable, If it is an ordinary variable, then we have to use dot. Okay, then that element is returned. That's it. Then comes main function. Here we are declaring two variables I and k. So first we are making that the stack pointer is pointing to that memory where where one element can be stored. Okay, where one variable of type element can be stored. Then we are creating some elements, six elements we are creating. Okay, 0 to 5. Okay, as an array. E of 0, E of 1. Okay, element, element is a user defined data type. For that, we are creating six elements. Okay, then we are running a for loop for I is equal to 0, I less than or equal to 5, I plus plus. Uh, in E of 0 for E of 0's key, we are storing 0. Okay, and then we are pushing E of 0. So initially stack size is 1. So this one element can be pushed. So it will say it is pushed. But then, okay, this should be I. Okay, this should be I. Okay, E of I. Then second time, E of 1 is equal to E of 1 dot key is equal to 1. That is 1, and we are pushing E of 1. But when you push for the second time, stack is already full. So that full function will be called. Okay, so it will display doubling stack size from 1 to 2. So that is from 1 to 2, and then it will double the stack size by using reallocate, and then the value will be pushed. Like that, it will push all the six elements. Okay, like that, it will push all the six elements, right? Okay, then we are trying to pop. So for pushing, we are writing like this: for I is equal to 0, I less than or equal to 5, I plus plus. So this loop will repeat for 6 times, 0 to 5. But in the pop, I'm trying to pop 7 times, 0 to 7. Okay. So the last pop will fail. So we are k is equal to pop, whatever the value it returns, we are displaying. So the last pop will fail. So to show the execution of that, we are popping for 7 times. Okay. Saving this. So the respective, what you call, WSL GCC code is here. Control X. This is the code. You can see here whatever I have showed in the notepad. It's the same code, nothing else. There is no change in this code, right? Okay, fine. Let me compile. This should be E of I. Okay, this is E of I. This is also E of I. This is also E of I, right? Control O. Dot slash dynamic. Let me clear this. Dot slash A or R. That's it. Okay. So first 0 is pushing. Okay, but initially stack size is 1. So 0 got pushed easily. Then it is saying doubling stack size from 1 to 2. Then 1 got pushed. Okay. Now it is saying doubling stack from 2 to 4. Okay. So another two elements it pushed comfortably. Okay. Then it is saying doubling stack from 4 to 8. But we are not pushing 4 elements. We are pushing only 2 more elements. Okay. So 0, 1, 2, 3. But it will allocate. It will allow us to push uh, 2 more elements. Okay. But current stack top is the fifth element. So when you pop, it pops out 5, 4, 3, 2, 1, and 0. Finally, after seventh time when you try to pop, it says stack is empty. Fine. Okay. Let us stop here. Thank you.